So a function has an inverse if and only if a function is one-to-one. We can make non-one-to-one functions one-to-one by restricting their domains. So examples of one-to-one functions and non-one-to-one functions are like x cubed and x squared. One is one-to-one and one is not. So we determine if a function is one-to-one by using the horizontal line test. The horizontal line test says a function is one-to-one if and only if no horizontal line intersects its graph more than once. What that means in general is that for every y, there is only one x. And for every x, there is only one y. So are the following functions one-to-one, yes or no? So go ahead and give me a rough sketch of x cubed and a rough sketch of x squared. So again, x cubed has 0, 0, 1, 1, 2, 8, and that has -1, -1, and -2, -8. So we know that x cubed is symmetric about the origin. It's up there in red. It is one-to-one because for every x and y, there is only one x and y. So again, x cubed goes -2, -8, -1, 1, 0, 0, 1, 1, 2, 8. However, x squared is not one-to-one because at 1, -1, 2, -2, 3, -3, you get all the exact same y values. So f of x equals x squared is considered an even function. So we talk about even and odd strictly because evens are never one-to-one. An even function will never be one-to-one. An odd function is usually one-to-one. And then we can find inverses algebraically. So we're going to talk about two methods in calc for finding inverses. We're going to talk about the first method being the algebraic method, where you switch your x and y's, solve, and then you can take your derivative. So that would be our method 1. So you first determine if the function is one-to-one, then you switch the x and the y values, solve the equation for y, and then find your new domain and ranges, and you can always verify that they are one-to-one by doing their composites. The composites of two functions are one-to-one if and only if you get the identity function. So f of g of x equals x means they're the identity. And that one AP classroom problem that we looked at, like where it was equal to x, this is actually the shortcut method for it. However, it also works long. So that's like kind of what we're going to see. Is there a formula? Yes. And then can you do it the long way? Yes. So two ways to get to the same conclusion. So show that the functions are inverses of each other, and then sketch both functions on the same set of axes. So you have f of x equals 2x squared minus 1, and g of x equals the square root of x plus 1 all over 2. So to algebraically show that they are inverses of each other, you are going to show that f of g of x is equal to x. So f of g of x equals x. You have to also show g of f of x equals x. So what happens when you take the square root of something squared? It is equal to the absolute value of x, not x. So we were all good and happy here. So composition was equal to x. But then what happens when we do its inverse composition? It's not equal to x anymore, it's equal to the absolute value of x. The absolute value of x is not x. So these are, by technicality, not true inverses. And that should make sense, because this original function is even. Even though it's shifted down 1 unit and comes on neither, it's an even powered function, so it's not going to be 1 to 1. So the only way to make that function truly an inverse and make it 1 to 1 would be to restrict its domain. Now, we could still graph them and still see that they end up looking like inverses and they follow inverse properties. So 2x squared minus 1 is going to be shifted down 1 unit. The 2 is going to stretch it. So instead of going up on right 1 and up on left 1, it's going to go up 2, right 1, and up 2, left 1. So if I make each of these points multiplied by 2, and then usually it goes up 4 in right 2, so that's going to go up 8 in right 2. The g of x graph, every point on the red graph should be a reflected point on the g of x graph. So by definition, inverses split the domain and range of their partner function. So if the original function has the point 0, -1, the inverse has the point -1, 0. And if you plug -1 in here, you get -1 plus 1 is 0, 0 divided by 2 is 0, or 0 is 0. So you can confirm that algebraically. And then if you have the point -1, 1, the inverse point should be 1. And here's why they aren't true inverses. Does the point 1, -1, exist on g of x? No. Can I ever get a negative g value? No. So I'm only going to get half of the inverse function. That's why they're not true inverses. Because the absolute value makes this all positives. So they're not true inverses because you only have the top half of the square root function. Which means that it's only really reflective or inverse to half of the square function. So what could I do to f of x to make that inverse as a function? I could restrict its domain. So would I want the positive half or the negative half? because the square root's positive. So if I were to restrict f of x's domain, I would want x values greater than or equal to 0. Because again, these points over here don't exist. I don't have -2, -7. I don't have -7, -2. I only have the positive part. So to make them actual inverses, you would restrict your it. That would actually, by making them x greater than or equal to 0, eliminate the need for absolute value terms, because everything you plug in is already positive values. Find the inverse of x cubed plus 2 using our algebraic method. So it's switching your x and y's and solving for y. Get rid of something cubed, you take the cube root. We are certain two things are inverses of each other if their domain and range are flipped. So we are certain two things are inverses of each other if their domain and range are flipped. That's what you call the reflexive property of inverse functions. You can also confirm algebraically by doing function composition. So in example 3, if I did function composition where I put f of g of x into g of f of x, and vice versa, if I take x cubed plus 2 and I put the cube root of x minus 2 into it, I get x, and same with the converse. So really, we haven't talked about calculus at all yet. We've talked about inverses. And it's important to have that understanding of inverses as we build in to the importance of inverses and calculus. So we are going to try to come up with a method for finding inverses in calculus that relates to their slope, because a slope in calc is a derivative. So the derivative represents the rate of change. So we're going to try to come up with a relationship between inverses and their rates of change. So, doing no calc whatsoever, we can graph the line y equals 4x plus 1. Just looking at that, you already should know what is its rate of change because this is linear. So y equals 4x plus 1's rate of change is 4, because that's the slope of the line. So graph the inverse function. So the inverse function of 4x plus 1 is going to be all the reflected points, or again, you can go off to the side and say, okay, x equals 4y plus 1, x minus 1 equals 4y, y equals 1/4 x minus 1/4, and ooh, those are gross points. Who the heck wants to start their x or y intercept at 1/4? So again, I would look at that and say, okay, well, if I plug in x equals 4, I get rid of one part but not the other, so 2 doesn't help. So really, I'm playing a game of there's no nice points. But if I take into account the inverse, if the original function has 0, 4, then its inverse should have 4, 0. So I plug in 1/4 minus 1/4 is 0. And then if you plug in 1, 5, it's like plugging in 5. So 5/4 minus 1/4 is 1. So then that one's good. 9, 2. There we have it. So on my graph, you can see I drew in a really dark line. So that line I drew in is y equals x. Y equals x, once again, represents the identity, right? Y equals x is the identity. If two functions are inverses of each other, they equal the identity. So if the two functions are inverses of each other, they're also going to be symmetric or cut in half by the identity. So if I folded my graph in half at y equals x, the purple and orange would sit on top of each other. So inverse functions reflect each other across y equals x. So we graphed its inverse. What is the slope of that inverse function? 1/4. So the connection is going to be between the 4 and the 1/4. So if f prime is equal to 4, its inverse slope is equal to 1 over 4, aka 1 over f prime of x. So it's going to be equal to 1 over its derivative. So the inverse derivative is going to have a relationship with 1 and the derivative of the original. If 2, 9 is on the original line, what point does it correspond to on its inverse? 9, 2. The slope of the line at 2, 9 on the original is the reciprocal of the slope of the inverse. The difference is that the slope of the inverse is calculated using the point 92 instead of 29. So that gives us our formula. It leads us into the fact that using concepts from derivatives and inverses, that if f prime of x at x equals a becomes df dx at a, and p and q and q and p are points on the inverses and the original, that the inverse derivative at p is equal to 1 over the derivative at q. So the inverse derivative at p is equal to 1 over the derivative at q. So on the original function is the point qp. On the original function is the point qp. F of x has the point f of q equals p. The inverse, which we say as f of inverse x, would thus contain the point p to q. We're all good for that, right? Like, that makes sense. That's what we just talked about with the 2, 9 and the 9, 2. So, the derivative of the inverse at p derivative of the inverse at p is equal to 1 over the derivative of the original at q. That's what that formula is saying. just like a different way of writing it. And I think sometimes that way is helpful. And I'll leave that helpful. So f and g are considered inverses if their points are all reciprocals. So let f of x equal x to the fifth plus 2x minus 1. We want to first verify that 0, negative 1 is on the original. So I want to show that f of 0 equals negative 1. If f of 0, negative 1 is on the original, then what point is on its inverse? The inverse contains the point f inverse negative 1 equals 0. If 0, negative 1 is on the original, then negative 1, 0 is on its inverse. That's what that says. So if I want to define f inverse prime at negative 1, the derivative of f inverse at negative 1 is equal to 1 over f prime of 0. That's what that says. So we need to know what is the derivative. And then you plug in 0 to that derivative. And we get 1/2. The alternative method, it's not going to be fun to do. The alternative method would be using implicit. So implicit differentiation would say that if you wanted to find the inverse of this function without knowing your formula, well, what's the rule? The rule is you switch x and y. So that would mean that this becomes x, and then you get y to the fifth plus 2y minus 1. Now the rule would be to derive that. So derivative of x is 1, 5y 4 dy dx plus 2 dy dx. Take out your dy dx GCF, solve for dy dx. Holy moly, what does dy dx really look like? 1 over f prime of x. Boom, boom. So you can see it, but now what's the difference? Now the difference is that if this is my dy dx, this represents the slope of f inverse, or represents the slope of f inverse. So now if you're finding f inverse prime of negative 1 is my x, right? So what's the y? 0. So you're plugging in 0 for y. So you still need to take into account this idea that this is x and this is y. And then since this is in terms of y, you're plugging in 0, not negative 1. Everybody kind of like makes that mistake and they plug in negative 1 and then they get the wrong numbers because it like goofs them up, but it's a y, not an x. So you need to plug in the y value, not the x value. Does that make sense? So those are the two methods. This is like method 1 and method 2. Those are the two ways you're going to see these problems done. And then the alternative is like a table. But a table is just a manipulation of all of that. I feel like it's a lot to digest, and like it's so much easier once you start to do like a problem or two, because while I'm speaking, it's like, So then the next problem is f of x equals x cubed plus 2x minus 1. You are trying to find the derivative of the inverse at 2. So think about the fact that that goes back to this, right? So the derivative of the inverse at 2 means that the 2 is really the y value of the original. So I don't know x. So what I have to do in this example here is find x, knowing that 2 represents y. So I have to take the original function and set it equal to 2 and solve for x. So you get 0 equals x cubed plus 2x minus 3. Go back to algebra days and think about p divides q. So that's the factors of the last over the factors of the first. So looking at that last term, it's 3. So factors of 3 are 3 and 1. So I'm plugging in 3 and 1 to see if they equal 0. That's what I'm looking to plug in, because more than likely that's going to be my next number. They're not going to give you fractions and decimals unless this is a fraction, unless this is a calculator problem. If it's a calculator problem, we learned this the other day, what do? This becomes my y1, this becomes my y2, and I find the points of intersection. So if this was a calculator problem, y1, y2, points of intersection. This is not a calculator problem because it's going to be a nice number. So 1 plus 2 is 3. 3 minus 3 is 0. So my next number is x equals 1. So on the original graph, f of 1 equals 2. So on the inverse, or its derivative, f inverse of 2 equals 1. So if you're applying your formula, the derivative of the inverse function at p equals 1 over f prime of q. Well, q is my x value, which is 1. So I need to know what is f prime. So if nothing else, write a derivative down for me. If you could get it all, you can at least get the derivative point. And then say df inverse dx at 2 equals 1 over f prime of 1. So you get 1 over 3, 1 squared plus 2, which is 1. I like weird things and I like math. If you found f prime of 1 is equal to 5, so then like its derivative or inverse derivative is 1/5. So again, you can see that for 1/4, that reciprocal slope. So method 1 and method 2. Method 1 again is finding that derivative, finding its inverse point, and doing 1 over f prime. Method 2, I kind of already showed you, that's implicit. So implicit is considered method 2. That's where we take x and y and flip them, and then solve for dy dx. So, because why not? Let's do method 2. So flip x and y. find your derivative. So you have dy dx equals 1 over 3y squared minus 8y plus 7. So the derivative has all y's, but on the original I have all my x's, right? So this is like saying f of 1 equals So on the original, we have the 0.13. So my original x is 1, my y is 3. But what is the y on the inverse? 1. So I'm plugging 1 into my problem, not 3. Because again, that 3 is the y of the original. I just wanted you to be aware that this is like finding dy dx at 3, which equals 1 over 3 minus 8 plus 7. 3 plus 7 is 10, 10 minus 8 is 2. Which is a half. So f inverse prime of 3 is a half. Good? So what's nice about the implicits is if you know x, you don't really have to find y. If you know y, then you have to find x. But like if you're given x, then that's what you're plugging in. Now the next one is worded weird. Because it says find f inverse x at x equals 4. So now they're implicating that you're finding the inverse at 4, which is not the x value of the original, it is the x value of the inverse. So that's kind of like saying on the original, y equals 4. Does that make sense? So like that's why I said you have to pay attention to the wording. Like that says f of x at x equals 1. This one says the inverse derivative at x equals 4, but it says f inverse at x equals 4. So now it's a different implication. So f of x equals x squared, and they told you x is greater than or equal to 0. X is greater than or equal to 0, y is greater than or equal to 0. So that means on the inverse function that x and y are both also greater than or equal to 0. That allows this function to be 1 to 1. If that restricted domain wasn't there, if y was equal to 4, now you have two x answers. You have 2 and negative 2. So now you're at a loss with your inverse derivative. So here you have 4 equals x squared. So 4 is equal to the square root of x squared, thus 2 equals x. So 2 is my x value, then my y is 4, so in my original graph I have the point 24. On my inverse graph, that's the point 42. So then your derivative becomes x equals y squared. So derivative of x is 1, derivative of y squared is 2y dy dx. So dy dx equals 1 over 2y. So in this case, it's 1 over 2 times 2. So f inverse prime of 4 equals 1. That's 1 over 2 times 2. And again, going back to the original, the derivative of f of x equals 2x. So f prime of 2. So we're super happy because they make sense. So it's possible that method 2 can be streamlined a bit using the following formula. So we have f prime inverse of x equals f prime of f inverse x, but f inverse x is really just like the y value of the original. So again, that is even another way of saying this. Without putting in the cube here, it's the composition of f inverse of p equals q. So I streamlined it a little bit, the textbook does not. Last two. Find the derivative of the inverse of f of x equals 1/4 x cubed plus x minus 1 x equals 3 using that formula from above. So f inverse of that would be like saying y is equal to 3. So we still need to know what y is. So let's find f of 3. Okay, so then if we want to find the derivative of the inverse at x equals 3, then it's equal to f inverse prime of 35/4 equals 1 over f prime of f inverse of 35/4. Which is really like saying f prime of find the f prime. And then the last one is the table. So the table and the formula really go hand in hand with each other because, again, they make a whole lot of sense when you do a table with a formula. So the idea is that we have our original function. And we have G inverse prime of 1. So going back to this idea here, G inverse prime of 1 means that 1 is the y value of the original G. So you want to go to your table and you want to go to the G, and you want to find 1 as the original y, which means the x is negative 1. So that negative 1 is what we are going to look for our derivative at. So this is going to equal 1 over G prime of negative 1, which is equal to 1 over negative 1/5, which is equal to negative 5. So tables are fun. Like, they're easy. Okay, you have G inverse prime of negative 3, means negative 3 is the y value of the original, so that's like 1 over G prime of 4, which is 1 over negative 2.